Welcome to this video. It gives an overview of RF impedance matching design and simulation software from rfhammer.com. Save the exe and the icon file on your PC. The software is bundled into a single exe, so it could take a minute or two to open, but it should run on all standard Windows 10 machines. So the first window which opens is this one, where you can select between different types of matching networks. So we have an L section, pi section, T section, and bandpass filter section. Each one has options which you can select. For L section, pi section, and T section, we have low pass and high pass. Low pass being with series inductors to pass DC, and high pass with series capacitors to block DC. The bandpass filter case, we can select real matching, real complex matching, complex matching, and this is a tool which we can use for complex matching. Let's go to an L section and open a low pass. We can run this. So in this case we are matching Z load to the complex conjugate of the source for maximum power transfer. We have 4 windows here. So this is your input window, all the input parameters. This is your plot of your simulation, the Smith chart or the amplitude you can select. This is your circuit diagram, and these are your component values. The frequency plots are using the exact values, and your component values are truncated to 4 decimal values, 4 decimal points. Right, the input, we have the frequency, we have the source and the load, complex impedances. So this is a complex impedance of the source, 50 minus J10. You can make this real just by making your imaginary part 0. We have inductor Q, we have the system impedance, stop-start frequencies for the plot, number of frequencies. If you increase this, your plot can become smoother. A marker we can move around, and then you can select between a Smith chart and the amplitude. For example, here we see the amplitude. The Smith chart, so we have a plot of the load in brown, a plot of the source in green, and then in blue we have the Z-in of your matching network. And as expected for the center frequency, Z-in is the complex conjugate of the source. Right, so that's fairly straightforward. L section, you can more or less match everything, but you don't really have any control over the bandwidth. Right, let's go to a pi section. This is very similar. It has an additional input where you can specify the circuit Q. So it gives you a bit of control over the bandwidth. If you increase the circuit Q, your bandwidth becomes smaller. Right, let's have a look at the amplitude. Let's make this an ideal lossless matching network. So we make our Q very large. Making the Q large gives you lossless inductors. Okay, so here we now have a lossless network, and we can see the 10 dB bandwidth for a circuit Q of 3. Let's make that 10, so we can run that, and we see we get a much narrower bandwidth, minus 10 dB bandwidth. Right, so that's a pi section. We also have the capability of opening multiple windows. So let's open L section once again. So we have the same values. Now we can compare. Let's compare the bandwidths of the two cases. We have the same values here. Let's just make this a lossless circuit so we can run that. Let's look at the amplitude. Right, so here we can compare the amplitude of the L section and the amplitude of the pi section. So it's very useful to open multiple windows to compare matching network designs. Right, let's close these. I'm not going to go to the T section in detail. It's similar to the pi section, only here we have a T configuration for our network. Right, let's go to bandpass, real. So in this case we are going to match two real impedances. The source is real and the load is real. We have a circuit topology, so we can have a series element first for our matching network, or we can have a parallel element first for our matching network. Okay, we have the order and the ripple. Okay, so let's have a look at the amplitude. And if we change the ripple of the Chebyshev prototype, then we should get a better return loss. We get that as expected. And we can also make this in a higher order. Let's make that 7. We can run that. Let's make this an ideal lossless circuit by making a large Q. So there we have our amplitude of the 7th order. Let's look at the Smith chart. Right, so there we have the Smith chart. We have sliders down here to move our circuit diagram, and for the component values as well to see all the component values. Right, remember in this case we are matching Z load to Z source for minimum insertion loss. Right, so that was a real matching, real to real. Let's look at real complex. So in this case we have a real source but a complex load, and the complex load can either be in series or in parallel. So for this case, for example, we'll have a series resistor and a series inductor. This is positive, so it's an inductor. And for parallel, we'll then have a parallel inductor and a resistor. So we can. This is basically your equivalent circuit then of your load. Okay, so when we run this, we get our circuit diagrams. We get our responses, and as expected, if we make our bandwidth narrower, we're going to get a better match over the narrower bandwidth, so that you expect from a matching network. Right now, this design is based on absorption of your reactive part of your load into the matching network circuit. So and this absorption can either be exact or it can be over-absorption. So let's investigate that. In this case, let's have a look what the equivalent circuit of the load is. So this is a useful tool which we can use. Right, so in this case we have a load of 25 J125. So let's see what the equivalent circuit looks like. Sorry, it's the load of 25 and imaginary part of 125. Okay, 25, 125, and we have a series case, so series case, and we're doing the inductor. So over here we convert the impedance to the equivalent circuit. Over here we can convert the impedance to an RC equivalent circuit. This is an RL equivalent circuit. Right, so let's run that, and let's have a look then what we have for the matching network inductor value L5. So there we have a value of 331 nanohenry, and our load inductance value is also 331 nanohenry. So that's going to be exact absorption. So your inductor of your load is exactly absorbed by your inductor of your filter matching network. You can also have over-absorption. So let's change this to 25-25. Let's keep it inductors in series. 25-25, we run that. And here you can see a description telling us what's happening. So in this case, we have over-absorption on the output. Okay, so let's have a look at this load now. 25-25. So let's make that 25. It's still series, and we run that. Okay, so this is the inductor of our load. And for our matching network, we have a value of L5 of 79 nanohenry, and this is 66 nanohenry. So we have over absorption, and we must split L5 up into the value of the load inductor, and the remaining part will then become part of your matching network. Right, so that's an example of real to complex. Let's have a look at complex to complex. Okay, so in this case we have a complex source and a complex load, and each of these can either be in series or parallel, so we have 4 combinations here. And in this case we can either have overabsorption on one side and exact on the other side, or we can have overabsorptions on both sides. Okay, so let's have a look at this case. Let's run this. Okay, so it's telling us split input LC for overabsorption. So it's telling us the input is overabsorption, and then the output, so L5 will be exactly absorbed by your filter network, but over here we have overabsorption. So let's have a look then at that. Okay, so the input, we have a source of 50, 125. Okay, so let's make that 50, 125, run that. Okay, so here we have a value inductor of 331 nanohenry. The input we have a value of 383 nanohenry. So we must split this up into the value of the inductor of the load, and the rest becomes part of your matching network. If we had to look at the output, let's have a look at the load, that is 25. So let's make this 25, and we can run that. So in this case we have a equivalent load circuit with an inductor of 331 nanohenry, and we see that for L5 we also have 331 nanohenry. So that's the exact absorption. Okay, we can also then get the case where we have absorption on both sides. So let's make 25-25. Let's make this 25-25. We run this. And 50-25, so we make our source 50-25, and we run this. Okay, so let's just check 50-25 and 25-25, and it tells us that we have overabsorption on the input and the output. So that means we must split L1 and L5. Let's have a look at L1. L1 we have 50, and 25. And let's run. Okay, so here we have 66 nanohenry, and L1 in this case is a large value, so we have to split this up into the value of your source inductor, and the rest becomes part of your matching network. Let's look at the load. It's 25-25. We can run that, and we get inductor for our load of 66. In this case we have inductor of 79. So once again we must break this up into the value of our load inductor, and the rest then becomes part of our matching network. Right, I hope this video was informative, and remember to visit rfhammer.com.